Thank you. Thank you, Noah. Can I just ask, has everybody picked up a handout? Sorry? Yeah, please, could you? Yeah. Bring them in here so that, bring the whole lot in here. Thank you. Let me add my warm welcome to you all. This is going to be an exciting year for you, Part 1B, Material Science, and we are going to begin with one of the most exciting subjects, which is phase transformations and metals and alloys. I've prepared a really comprehensive set of notes for you, and there's an awful lot more of movies, etc., available on the websites that you've been told about. So I would think that there is a minimal amount of note-taking that you need to do during the lectures. So you can really focus on the presentation. And if you have questions, it's best to interrupt me and ask the questions at this time so that you get a full understanding of what's going on. So have a look at the notes when you get some time. They're pretty comprehensive, and I'm going to follow the sequence in these notes. Okay? Right, so today's lecture is specifically about diffusion. And diffusion basically means the mixing up of things. And of course, we know that when we put on a bit of perfume or aftershave, it spreads out rapidly. That's through a process of diffusion. And of course, there are other things like fluid flow, etc. So you might have air transporting those species which cause the scent. But diffusion also happens through the solid state. For example, if you had atomic hydrogen, you couldn't actually hold it in a cylinder of steel because it would very rapidly move through the steel and get out into the atmosphere. The only reason why we can put hydrogen in steel cylinders is because it's molecular hydrogen, which is much more difficult to penetrate the steel. So we'll figure out by the end of this lecture how atoms actually move even through solids, which cannot flow. The difference between a solid and a liquid is that a solid can support a stress, whereas a liquid can't. So flow can also transport species. So what I'm going to cover in today's lecture is, first of all, begin with the random motion of atoms, and then deal with some laws of diffusion. And I've put the laws in inverted commas because these are very well-established equations, but they are empirical. We'll prove in the second lecture that they are empirical and there's a better way of doing things. Nevertheless, for the vast majority of scenarios involving diffusion, these equations will work. I will derive a couple of solutions to the diffusion equations so that you can apply them to practical problems. And then we'll discover how atoms actually move in a solid and define the diffusion coefficient in terms of atomic mechanisms. At this point, I will also define the diffusion coefficient, but it will be an empirical diffusion coefficient. Okay, so first of all, what do I mean by random motion? This is the so-called problem of Brownian motion, for example. If you put a tiny polystyrene particle into, say, water, then it will not remain still. It will be knocked about by the atoms, and it will move generally in random directions. And this is illustrated in this little movie, where you see this particle executing Brownian motion. Some people call this also a drunken walk, Now, the thing about random motion is that there's an equal probability of going forward and reverse, okay? So supposing we consider random motion in one dimension, then what do you think will be the mean distance moved? 0, okay? So let's just go to the next slide. So supposing we consider one-dimensional random motion and the step length is lambda, then there's an equal probability of going forward and in the reverse direction because these are random jumps. So for my first step, I will have a length plus or minus lambda, and the mean distance traveled is 0. But the root mean square distance will be given by lambda. Okay? So this is just the root mean square distance. Everybody happy so far? Okay. Now supposing I take another random step, then I will have the root mean square distance as the distance from the first jump and the second step. When I square that, expand that, I get an equation like this, x1 bar squared, lambda squared, and this term here. Now, because this is 0, this term disappears, and I end up with just this, which is equal to 2 lambda squared. So if I take 2 random jumps, then the mean square distance is 2 lambda squared. If I take n jumps, it'll be n lambda squared. So the mean distance from the beginning to the end of a random walk will be lambda times the square root of the number of steps that you take. Now this equation is actually quite important. For example, when you have a polymer chain, and the polymer chain consists of small molecules joined together, then each molecule can be regarded as one of these steps, and the end-to-end distance of that chain will be given by lambda, which is the size of each individual monomer, and the number of monomers that you've linked. Okay? So the mean distance moved in a random walk is lambda times the square root of the number of steps that you take, the number of jumps. Okay? Now, we can change this term, the number of steps, and express it in terms of a frequency, how many times per second you take a step. So if I take the frequency and multiply by the time, then that gives me the number n. Yeah? So all I've done here is replace the number of jumps by the frequency multiplied by the time. And this relationship, it goes through all of science. If you think about heat flow, if you think about electrical currents or diffusion and many other phenomena, you find that the mean distance is proportional to the square root of time. Okay, so it's a parabolic relationship. The mean distance that you travel in a random walk changes parabolically with time. In all of the equations that you'll see, you will always have a square root of time term. Okay, so now we've just looked at random walks. And diffusion, of course, doesn't just happen in random directions. You might have a concentration gradient, in which case there is a greater probability of diffusion down the concentration gradient. So we need to think about that. Before I do that, I'll show you this movie, which shows how, if we start with a cluster of atoms, how that cluster expands by this random motion. And that expansion of that cluster will vary with the square root of time. So at first it will be a rapid expansion, and then it slows down as you go to greater and greater times in a parabolic fashion. So here you can see that at first it expanded very rapidly, and then its size remains more or less constant. Okay? So again, this is the perfume analogy that I gave you. If there are no currents of air and you put some perfume on, then you can expect it to spread with the square root of time. Right. I explained to you that in general, when we talk about diffusion, we really mean diffusion through a concentration gradient of some sort. And to simplify things, we will first start with a concentration gradient which is constant. In other words, the variation of concentration with distance is a straight line. Okay? Now, the units of concentration are the number of atoms per unit volume. Okay? So concentration is defined as the number of atoms per unit volume. And what we want to do is we want to see what the flow of those atoms is down this gradient per unit of time and a cross-sectional area which is 1. Okay? So imagine that this is a bar of material extending in this direction, and that bar has a cross-section which is 1 square meter into the plane of the board. Now, obviously, the concentration at this point is greater than the concentration at this point. So we write this as C and C plus a change in concentration, delta C, as a function of distance. And these are planes of atoms which are separated by a distance lambda. So lambda is now our jump distance, which is the interplanar spacing if this is a crystalline solid. Now, you saw when we were looking at the stochastic motion of atoms that the atoms can jump in the forward or the reverse direction. So we have to look at the flux of atoms going in the forward direction and in the reverse direction, take the difference to find the net flux along the direction x. So the flux in going from left to right will be given by 1/6 times the frequency of attempts, the concentration, and lambda. Now, can anybody tell me why we have that number 1/6? Okay, so I'm now looking specifically at jumps from the left-hand side to the right-hand side. And remember, this is a bar, which means it's a three-dimensional object. Why do I have to scale? Yeah.
Because it can jump in any 6 directions, up, left, right, in, out.
Exactly. So there are 6 possible directions in this particular diagram where the atom can jump. So I only want to look at the jumps from left to right, and therefore I scale it with 1/6. Now, nu over there is the attempt frequency. That means it's jumping with a certain frequency in that direction. And I want to know how many atoms of the solute there are in this particular plane, and that plane has a thickness lambda. Okay. So concentration is the number of atoms per unit volume. We have a bar which has a section, cross-section, which is 1 unit area, and lambda is the thickness of that plane. So C multiplied by lambda gives me the number of atoms per unit area of solute on that plane. Okay? So this is straightforward. The 1/6 is because the atom can jump in 6 different directions. This is the jump frequency, and this gives me the number of solute atoms on this particular plane, because the thickness of that plane is lambda. Its cross-sectional area is 1, because I've taken a bar which has a cross-sectional area of 1 square meter. So lambda is actually the volume of that plane. If I multiply the volume of that plane by the concentration, I get the number of atoms of solute on that plane. Okay? Similarly, if I now look at jumps in the reverse direction, the concentration now is C plus delta C. So this equation is very similar to this, except now the concentration has changed. So if I want the net flux, which is defined along the direction x, then I simply take the difference between these 2 equations, and we get this relationship. Now, what I've done over here is I've changed delta C into lambda times dc by dx. Okay? So lambda is effectively the jump distance, and this is the gradient. If I multiply the gradient by the jump distance, I get the change in concentration. So here's the gradient. If I multiply it by the jump distance, then I get delta C, right? So if I now take the difference between these 2, I get a relationship like this, where I'm absorbing all of these terms into this equation, into this parameter d, which we call the diffusion coefficient. What you get is that the net flux is proportional to minus the diffusion coefficient times the gradient. Now, notice that there is a minus sign there, okay? And that's simply because the gradient here is negative, so the flux is happening down that gradient. Now, what is the assumption we have made in this derivation? The key assumption? Well, we have assumed that the flux is proportional to the number of solute atoms we have over here. Okay? So that's a fundamental assumption, that we are assuming that the flux will depend on the gradient of concentration. And that's a completely empirical assumption. We haven't justified it at all. It seems to make common sense, but I will give you an example in the next lecture where you will see diffusion happening up a concentration gradient. But in the vast majority of scenarios, 99% of all the cases that we deal with, diffusion will happen down a concentration gradient. But there are some very, very interesting and useful examples where it can go uphill. Okay? Now, this is known as Fick's first law of diffusion, that the flux, which is the number of atoms per unit area per unit time, is proportional to the concentration gradient multiplied by the diffusion coefficient, and there's a minus sign because this gradient is negative here. Okay? So this is Fick's first law of diffusion. And it's expressed usually in a simple form that we have the flux, the diffusion coefficient, and the gradient. And I absorbed the jump frequency and the jump distance and the 1/6 term into this single parameter d. Now we know from the random walk analysis that the mean root mean squared jump distance is proportional to the square root of time, the square root of frequency, and the jump distance lambda. So if I substitute in here, you can estimate a rough diffusion distance if you know the diffusion coefficient. Okay? So you can find diffusion coefficients, collections of diffusion coefficients in data books. And if you want to work out the rough distance that an atom might diffuse in a time t, then you simply say it's root 6 dt. Okay? So that's a very good way of working out a rough diffusion distance. An order of magnitude approximation, because we haven't got any gradients, etc. in here. Okay? Okay, now let's remove the approximation that the gradient is constant. See, in the previous analysis, the concentration varied with distance as a straight line. Okay? Now we are looking at a concentration variation which is not linear. So if I take the same bar and I look at two cross sections here, each of unit area, then the gradient here is different from the gradient here. So the flux going into crossing this plane 1 will be different from the flux leaving plane 2. So what will happen to the concentration in this region? Okay. The flux entering plane 1 is going to be different from the flux leaving plane 2. So you've either got to get a buildup of solute or a depletion of solute, depending on how the concentration varies with distance. Okay? So no longer will the gradient of concentration remain constant. This will actually change with time. Okay? So what we are going to do is we're going to apply Fick's first law to this plane and then apply it to this plane and take the difference between the two fluxes. The difference between those two fluxes will tell us how the concentration in this region changes with time. Okay, so the flux going into plane 1 is simply the diffusion coefficient times the gradient, and this time I've got a subscript 1 here to indicate that this is the gradient at position 1. Okay? Previously we didn't need to use that because the gradient was constant. For plane 2, the flux will depend on the gradient at location 2. Okay? And I can expand this term. I can write the gradient at point 2 in terms of the gradient at point 1 plus a change in gradient with distance. Okay? So this is how the concentration gradient varies with distance. When I multiply it by distance, I get the gradient at point 2. Okay, is everybody happy with this? Yeah. All I've done is I've expanded the gradient at point 2 in terms of the gradient at point 1 and a change in gradient with distance x. That's why we have this d squared c by dx squared, because that tells me the curvature of that line. Okay? So in the next step, all I have to do is take the difference between these two to find the change in the number of solute atoms in that region with time, okay? Because flux has units of solute atoms per unit area per unit time. So am I going too fast, or is this a reasonable speed? Okay, so complain if I go too fast, okay? Okay, so if I take my change in concentration in this region, delta C by delta X, that tells me how many solute atoms there are in that region. Flux in, flux out, the difference between those two multiplied by time balances with this side, and therefore I get the change in concentration with unit time being equal to d times the curvature of that line. Okay? So now we've got the concentration changing with time, and the rate at which that concentration changes depends on the curvature of that line. If that curvature, d squared c by dx squared, is 0, then I don't get any change in the gradient within that region, okay? Because there's no buildup or depletion of solute. So this is Fick's second law of diffusion. And really, those two equations, you can deal with 99% of all cases where we have diffusion happening. So for example, if you're doping semiconductors, or you're introducing certain species of atoms into the surface of a metal, these equations serve extremely well. But again, you see, Fick's second law relies on the assumption that the flux varies with the gradient of concentration. Okay? You might think that really it should vary with the gradient of free energy, because free energy is what determines equilibrium. Yeah? The reason why diffusion really happens is that it's trying to make the free energy uniform everywhere. Okay, so we've dealt with the random motion of atoms, and we've dealt with the laws of diffusion. And now I'm going to derive solutions for these two diffusion equations for specific scenarios. And although I'm going to show you two solutions, it really amounts to a single solution, okay? So I'd like you to pay attention, because I want to explain to you the meaning of a particular mathematical function. Okay, so first of all, we are going to start with a scenario in which we have a thin layer of solute plated onto a bar which extends to infinity in one direction. So we call this a semi-infinite bar. Okay? We've got a thin layer of solute plated onto a semi-infinite bar, and we are going to allow diffusion to happen. So at time 0, we simply have a certain amount of solute plated onto the surface of this bar. And that amount of solute that we've plated is given by this constant value, B. Yeah? Now, obviously, we've got to conserve mass while diffusion happens, right? So what would you say? Can you say anything about the area under this curve? So this is at time 0. This is what happens at a small time later and a further time later. Has to be constant, doesn't it? Because we are not putting any more solute. We've simply plated a layer, and then we allow it to diffuse. So one of the boundary conditions is that if we integrate the area under the curve, it must come to the starting amount of solute that we've plated onto the surface. Okay? Follows from the conservation of mass. And before diffusion begins, of course, there is 0 solute in this region. So the second boundary condition is that when x is equal to 0 and time is equal to 0, the concentration in this bar is 0 because we haven't allowed diffusion to happen. If I take my Fick's second law, because this is not steady-state diffusion, the gradients are not constant, so I have to use Fick's second law, then if I write an equation of this form, it will satisfy these boundary conditions. So if you derive d squared c by dx squared, okay, you differentiate this equation, it will satisfy Fick's second law. Now, notice here, we have x squared over t. Do you remember that we saw that x will vary with square root of time? The diffusion distance will vary with square root of time, or you can say x squared will vary with time. So in here, you have x squared over t. Okay, so that comes from the first few slides that I showed you, where the mean diffusion distance varies with the square root of time. So always when you see an equation like this, you will have x squared over t, or x over square root of t. Okay, let me show you how this profile develops. So that was very quick, but it started off very high, and now it's simply carrying on diffusing. Now time is reversing in this particular graphic that I have, okay? Basically, it spreads out over a longer and longer distance with time, because we have a semi-infinite bar. If I had a finite bar, then the concentration at this point would start rising, but that's a much more complicated thing to deal with, okay? So we've got this exponential solution, and we started with a thin layer plated onto a semi-infinite bar. And there are many, many examples in practice where you do an experiment like this, or even in production, where you plate something onto the surface and then it's allowed to diffuse into the material because you want to change the surface properties. Okay? We'll come to those examples later. But I now want to deal with another case where I have a diffusion couple. That means I have two semi-infinite bars of different materials joined together. So on one semi-infinite bar, I have, say, copper. On the other side, I have zinc. How can I do that? Well, supposing I start with this solution. That means I have a thin layer of copper plated onto zinc. Then I plate another thin layer on top of that. And I continue doing that. Then I will generate a semi-infinite bar of zinc, copper on the other side, right? So does that give you a clue on how I could derive the diffusion solution for that scenario? So I start with a thin layer, then I'm putting another thin layer, building up the bar of copper on the other side. Okay, so this is our exponential solution, where we have a single thin layer plated onto a semi-infinite bar, and you saw that as I vary time, it spreads out, okay? So this is the equation that I'm plotting. If I now put several thin layers on top of one another, then it's like adding lots and lots of exponential solutions. Okay? So if I want to make a thick layer instead of a thin layer, then all I do is I have my first thin layer. My second thin layer is plated on top of that, so I displace it with respect to x. Okay? Third layer is plated onto the second layer, so I've displaced it again and again, and I can continue this. And just to show you what that looks like, yeah, you can see these are just 4 exponential. Okay. So once again, apologies for that. But what I've done here is I've superimposed 4 exponential functions displaced from each other by a certain distance, because we are plating one layer on top of another. And you can see I'm creating a bar which can extend to infinity if I add an infinite number of exponential functions. Okay? So if I take these functions, displace them with respect to each other, and then integrate, I get what's known as an error function. Okay, so all we are doing is taking exponential functions, displacing them relative to each other, and integrating from naught to infinity in the other direction. And that is the meaning of an error function. Okay? It's simply the addition of all these exponential functions so that I can treat a problem of this sort, where now the concentration starts off as a step function, and then as diffusion is allowed to proceed, it evens out. So this isn't really a separate solution. It's simply the exponential function adapted for a diffusion couple. Okay. Everybody happy with that? So I want to build this up, yeah? So I'm going to integrate from naught to x, depending on which side I'm building up. It could be naught to x or naught to minus x. But this is the error function plotted, okay? And this is a very common problem, again, where you put two different materials together and then you put them into service at high temperatures, and you will get the diffusion of matter from one side to the other. And of course, the boundary conditions for this, basically, supposing you start off as a step function with no diffusion at all, then the concentration when x is 0 and time at any time will be Cs, because that point remains fixed. Okay? We've got equal fluxes going, and therefore the concentration in the middle doesn't change, and the concentration far away will be this value C naught. So when we put those boundary conditions, we get the variation in concentration here as an error function. Notice again you have x over square root of t. Okay? So those are the only two solutions that you need to know, and they cover the vast majority of scenarios. Everything else, is more complicated because we deal with finite sizes instead of semi-infinite sizes. So the concentration far away from the diffusion will also change. Okay? Here we are assuming that the far field concentration doesn't change, and that's why we have this approximation. Okay, so far we've dealt with diffusion basically in terms of mathematical equations, and it's known as the phenomenological theory of diffusion because it doesn't actually tell us much about how the atoms are moving about, but it describes the variation of concentration. This slide actually shows you two particular mechanisms of diffusion. Here we have a very small atom inside of a material, and it's lying within the interstices inside your crystal. So can you give me an example of an interstitial atom which you commonly find in crystals? Exactly, carbon in iron. And this is a case where we have substituted a solute atom onto the main lattice. Okay? So this is a substitutional atom, and for this to move, you require a vacancy to exist inside the crystal. Okay? So for it to translate from one point to another, you need a vacancy. We will prove that shortly. Okay, so this is an animation of self-diffusion. You can see that it involves the migration of vacancies. And once, in these movies, when you see an atom moving, it looks as if it's effortless, but there is an activation barrier in going from one position to the other, because as the atom moves, it's got to push some of its neighbors out of their normal equilibrium positions. Okay? So that's self-diffusion. Self-diffusion means that it's happening in a pure substance. Okay? So supposing this is copper, then the copper atoms are simply diffusing within a copper lattice. And this is interstitial diffusion. And interstitials generally fit very badly inside the holes in the crystal, so the distortions involved are somewhat larger. But there's a huge number of interstices available in the lattice, yeah? Whereas there's a very, very, very few vacancies available in a usual crystalline lattice. So interstitial diffusion tends to be faster. And this is to illustrate the meaning of an activation barrier. So when we say that the energy of this material is so much, that energy is not uniformly distributed. There will be a certain distribution of energies within that. So even if we have a barrier to atomic motion, some of the atoms will be able to make it over that barrier. Others will attempt the jumps, but not actually succeed in very many of those jumps. Okay? So there's a difference between a successful jump and an attempt frequency. Okay? So the attempt frequency is always lower than the frequency of successful jumps. And we've got to take that into account. So this is the attempt frequency, nu naught. So in a crystalline solid, you could equate that to the Debye frequency, which is the vibration frequency of atoms. Okay? This is the probability of that jump being successful. So G star is the height of that activation barrier. It's the free energy, the activation free energy for that barrier. So if I multiply the probability of a successful jump by an attempt frequency, I get the real jump frequency. Okay? So this is just a normal Arrhenius equation. Yeah? You happy with that? I can expand that activation free energy into an activation entropy term and an activation enthalpy term. And in the books, they usually write this as Q, an activation energy. But what they mean is an activation entropy, and this part of this relationship is independent of temperature. Okay? You know that G is equal to H minus Ts, and that's why T has disappeared from this side of the equation. Okay? So this is independent of temperature, and this is temperature dependent. And given that the diffusion coefficient is proportional to nu, we can write the diffusion coefficient as d naught, which is the temperature independent term, and the temperature dependent term. Okay? So this is the classical way in which diffusion coefficients are expressed. There is a temperature independent term and an activation energy term. If I take the logarithm of the diffusion coefficient, then I will get a straight line if I plot against 1 upon the temperature. Okay? And here are some plots. So this is the logarithm of the diffusion coefficient versus the reciprocal of the temperature, and you can see straight lines. Now notice that the interstitial diffusion coefficient is very, very much larger than that of substitutional atoms. Remember, this is 1 upon the temperature. So low temperatures correspond to high values here. And you can see that at any temperature, interstitial diffusion is much faster than substitutional diffusion. Okay, now, how do we know that diffusion happens by a vacancy mechanism of substitutional atoms? If you work out the equilibrium concentration of vacancies at room temperature in iron, it'll be about 10 to the minus 10. Okay, so that seems very, very, very small to account for the diffusion that we observe. So there was a huge amount of controversy on how atoms actually diffuse in a solid. Many people were proposing that atoms simply exchange places. So one atom moves that way and another one moves that way. Now that would cause a lot of distortion in the lattice. And you would also have to have correlated motion. Okay? So then the argument became that, okay, we'll have a ring of atoms moving, because if you have a ring, then the distortions are smaller, but then you have to correlate the motions of a lot more atoms. So it wasn't terribly convincing until there was a very, very beautiful experiment done by Kirkendall. Okay? What he did was he made a diffusion couple. So on this side, we have an A-rich material. On this side, we have a B-rich material. And the diffusion of A in B is faster than the diffusion of B in A, because they are different crystalline substances, right? So diffusion coefficients don't have to be identical. But before he started the experiments, he put some inert markers. So this was actually a copper and a zinc diffusion couple, and you put molybdenum wires in the middle and fixed them to the laboratory bench. Okay, so that's a unique position which doesn't change during the course of the experiment. So those are known as Kirkendall markers. Now, if you have a greater flux in this direction than in this direction, then the whole specimen should move on your laboratory frame, right? Laboratory frame is your molybdenum wires. And sure enough, the specimen was observed to translate as diffusion happened. Now, this can only happen if it's a vacancy mechanism, because if it is a place exchange, then you must have equal fluxes on both directions. You know, if you're swapping a copper atom with zinc, then the copper atom moves that way and the zinc atom moves that way, and you cannot get a net translation. Okay? So this is a unique and very, very elegant experiment which proves beyond any doubt that diffusion happens by a vacancy mechanism in the vast majority of crystalline substances. The other consequence of this, in this case we are looking at copper-nickel couples, is that if you have a greater flux in one direction than in the other, then there will be a greater flux of vacancies in one direction than in the other. And those vacancies will condense to form holes. Okay? So you can see after this has been annealed to get diffusion, you get lots and lots of holes in the copper regions, which absorb a lot more vacancies. Okay? Because the diffusion of nickel, the flux of nickel is greater than that of copper, so you end up with more vacancies in the copper region, which condense as holes. Similarly, this is a superconducting cable made from the niobium tin compound. Okay? So Nb3SN. And these niobium tin wires are inside a copper cable, because if superconduction breaks down, you still have some conduction supported from the copper. Now, niobium tin is a very brittle compound, so you can't actually make wires out of it. On the other hand, niobium is very ductile. Okay? So what you do is you make a bronze. Bronze is copper tin. You drill it, you put niobium rods in it, and then you draw the whole thing out into a cable, because both bronze and niobium are ductile. You then allow the tin to diffuse and react with the niobium to form the superconducting compound. What you end up with is porosity. You see all these holes? That's, again, because the diffusion coefficients of niobium and tin are so different that you will get a net flux of vacancies which creates holes. Okay? Now, it actually doesn't matter in this application. And there is another application where we want to produce metallic materials which absorb a lot of sound. Okay? So sound barriers. And how do you introduce controlled porosity? Well, you can introduce using the Kirkendall effect. So you design your metal with particles, which then particles which are rich in solute, and the diffusion coefficients are very different. Diffusion itself will then create the porosity, which allows damping of vibrations. Okay? Any questions? Okay, in the next lecture, I'll try and demonstrate to you diffusion which can go up a concentration gradient. Okay? Thank you very much.